The speaker today, Thomas Roth, works for a company called Landwork AG, a security and software engineering company located in Germany. And most recently, the work that he did is actually involving encryption in cloud environments. Today, different topic. He's going to be talking about SPDY, a web protocol, I think written by Google, right? Yeah. Google guys? Yeah. So it's called Analyzing SPDY, Getting to Know the New Web Protocol. Please join me in welcoming Thomas Roth.
Hey, hello, welcome from me. Analyzing SPDY, or SPDY, how it's actually called, next generation web protocol, maybe. So let me introduce myself. My name is Thomas Roth. I'm mostly doing low-level programming in C, assembler, so mostly Unix stuff and on embedded systems and so on. You can find me online at Twitter, just Stack Smashing, or my blog, stacksmashing.net. First off, my journey to Vegas was a bit crazy. I missed 2 connection flights and was finally waiting for my bag to arrive. And what I actually got was this, which is basically this. And they were like, yeah, but don't worry, we gave you a t-shirt with it so you won't be naked. And I think I could actually wear it as a dress tonight. So due to that, I don't have my Linux machine with me, so I won't be able to present some of the practical stuff, because yeah, I spent the last night hacking on this Mac to get it somehow working, but the internet connection here doesn't allow me to check out a 1.3 gigabyte Git repository, unfortunately. So bear with me, but I give my best. So first, a small disclaimer. SPDY is work in progress, so everything I talk about may change. It's not yet a finished standard. We are at draft version 3, but Google is already using it like hell. And yeah, if you want to check the information, go to chromium.org and read the spec. And please contact me if something is wrong or if I should clarify something. So, 40 slide. Let's get started with what is SPDY. SPDY is a new web protocol, a replacement for HTTP, and was designed by Google to speed up the load time of websites. It tries to fix the problems and limitations that were introduced through HTTP because of the way we are using HTTP today. SPDY is basically SCTP over TCP. SCTP is a stream control transmission protocol. It's basically a way for transferring multiple data streams at the same time over a single connection. If you're actually using Chrome, you're likely to use SPDY already with every Google service like Gmail or Google Apps or whatever. And yeah. So let's talk about the modern use of HTTP. HTTP was designed for downloading single files. It works great for downloading an ISO image, it works great for downloading a single HTML file, but our modern web experience is mainly influenced by using many resources, like we have images on our websites, we have videos, we have CSS, we have JavaScript, and a single site actually takes 77 requests or even more sometimes. And yeah, that's pretty bad because HTTP does only allow pipelining. So you can't request several resources at once and download them at the same time. If you request a resource from a web page, the request blocks. You won't be able to do anything until the server has finished doing your request. So if you do a large search on Google or something, okay, Google actually has working infrastructure, so don't worry. If you request like pushes on a large SQL query, your whole connection will just block and you won't be able to continue loading the other resources that you may already could load if it wouldn't be blocking. Our modern workaround for this is using multiple TCP connections. Like modern browsers mostly have 6 connections at the same time open just because HTTP is not able to handle this. And there are, oh, thank you. Sorry. Kind of nervous. And there are also other circumventions like using multiple subdomains to allow the browser to load as many resources at once. This is something I actually saw at the customer side. He had like the dynamic1.example.com, dynamic2, static image, static data, because their front page was loading with 140 requests. And it took on a modern browser like at least 30 seconds without using this domain sharding. Another problem of HTTP 1.1 is the header handling. With every request you do, with every image request, with every CSS request, with every JavaScript request, you're sending the headers again and again. So if you have like 4 kilobytes of cookies in your browser, you resend them with every single request you do. There's no way to actually compress the headers. We have content compression like gzip or deflate encoding, but there's no way to actually compress the headers, and that's an overhead from 1 kilobyte to multiple kilobytes per request. And that's a lot of bandwidth wasted. The next problem that actually really kicked in with all the Ajax stuff going on is there's no server to client notification functionality. The server side has no way to actually tell you that you've got a new mail. You have to continue polling and polling and polling the server side until it says, yeah, you got a new mail, now stop going on my nerves. So that brings us to SPDY. What is SPDY? As said, SPDY was designed by Google for replacing HTTP, and if you're using Chrome for Gmail or something, you're already using it. Take a look in Wireshark, you will see a lot of cryptic stuff going on. And it tries to lower the amount of TCP connections. As said, with SPDY, you will only use a single TCP connection. You won't be using like 6 at once or something. And it's not only the fact that blocking TCP connections are a problem, but it's also that the round trip time really kicks in. If you use like 6 connections, you may have 2 connections which are decent, fast enough for being used as request pipeline. And you may also have several connections which are just too slow to be used because of the different routes your package will take. SPDY does also deliver server-side push functionality. So if you have your Gmail window open, you don't always have a request in the background asking Google if you have new mail, but Google will actually tell you. And SPDY tries to keep the compatibility with all existing web applications by just replacing the web server and the user agent. So if you actually want to change your infrastructure to using SPDY, you won't have to change your applications, just maybe your load balancers and so on. So SPDY has built-in header compression. All headers sent, no matter what you do, every header you send via SPDY is zlib compressed using the deflate functionality. And if you request like 10 resources, you can do the request at once, and SPDY will multiplex the TCP connections, so you will load all the data at once and not only serial. It also enforces the client to support compression. If you browse the web and just have some kind of sniffer open, you will see that a lot of sites still don't use gzip compression, and that's pretty ugly and pretty bad because you don't want to load uncompressed data anymore. I mean, we have like dual core CPUs in mobile phones. I think we have enough computation power for that. So let's talk about the architecture of SPDY. SPDY consists of 2 parts. There's the underlying framing layer and the HTTP layer. The framing layer is pretty generic. Even though Google says, hey, don't use it for other stuff, we built it for HTTP. It's also perfectly suited for almost anything where you have to transfer multiple data sets at the same time. The HTTP layer is basically on top of that framing layer and just implements stuff like cookies and header stuff and so on. We will take a deeper look at that at a later point. So a bit of terminology. The framing layer uses a single TCP connection, and this framing layer connection is called session. So if you go to a website, you create a SPDY session to this website. And on this session, you will transfer frames. And these frames basically are the representation of HTTP requests and responses in SPDY. It's very generic, so it doesn't feel like HTTP while working with it. And you can actually use the framing layer for other evil stuff like cache poisoning and so on, which we'll see later. Multiple frames that correlate to a single request are organized in streams. So we basically have the abstraction of having sessions. In a session we have streams, and in a stream we have multiple frames constructing the data. So a SPDY session is a single TCP, or if you want to do it right, please use SSL at the presentation layer connection to the server. And sessions are pretty dumb. It's basically just a small state object in your memory. The only functionality that the session itself delivers is you have persistent settings. Session-wide settings are basically predefined setting types like upload bandwidth and download bandwidth, which can be used by the server to optimize your requests. Like if you're going to a website and you say, hey, my download bandwidth is very limited, please give me a low bandwidth site like no flash and so on. That allows the server to do optimization on that site. It also keeps track of stuff like round trip time and the maximum number of concurrent streams. So the server won't try to push you 10 resources at once if your browser may only can handle 5 because your memory on your mobile phone is very limited or whatever. The cool thing about the settings are that they can be persistent. So based on an origin policy, like if the request comes from the same IP and the same user agent and so on, these settings are safe. There are also client-side and server-side settings, but one type of them is not yet used, but actually already implemented, and we can do some nasty stuff using that. So to the framing layer, there are two different frame types in SPDY. One are the control frames and one are the data frames. Each frame consists of an 8-bit identification header, and the first bit on that frame, on that header, determines the type of the frame. 0 is for data frame and 1 is for control frame. A data frame looks basically like this. You have the 0 as the first bit telling you, okay, that's a data frame, and then you have a 31-bit stream ID, which actually tells you to which data stream this data frame correlates. Then you have 8-bit of flags. Flags can be used to notify the receiver of the frame of several stuff like, okay, this is the last package that I'm going to send you, or this data is compressed, please use gzip to decompress it, and so on. The next field is the length, so it's 24-bit. It's limited at 24 bits, so you're likely to send multiple data frames if it's a large file. But as you can push as much data as you want, it's not really a problem. A data frame may has a length of 0, like if you do requests and the server determines, oh, the file is empty, it will just send you a data frame with a length of 0, but with a flag set, and that flag is flag fin, which determines, okay, this is the last frame I will send on the stream. After that, please don't do any requests or don't send me any data on this stream. There are actually two flag types for data frames, flag fin and flag compress. All data in SPDY is gzip compressed, so if you if you send accept encoding header to a SPDY application, no matter what you tell the server, it will answer in gzip. You won't be able to enforce it to use bzip or whatever. So this is how a control frame works. As you can see, the first bit is set 1. The next 15 bit are for version checking. Right now we are at version 3, at least draft 3. If you're using Google Chrome with Google services, you're still using draft 2, which is pretty cool because draft 2 still has some bugs and some cool things in it that allows us to hijack sessions and stuff, which is what we'll see later. The next thing is a 16-bit type. There are multiple control frame types, like there are control frames for managing streams, there are control frames for sending the settings over to the server, there are control frames for doing some measurements on the connection, like you can use control frames to do a ping or to measure the round trip time, sorry. And you can also send 8-bit of flags and, as always, 24-bit lengths of variable data at the end. And, yeah. Important is that for each control frame type, you can have different flags. Like for the stream management control frames, you may have flags that indicate that your stream is unidirectional and so on. So yeah, you may want to keep an eye on that. So SPDY streams represent data connections between the client and the server. A stream can be uni or bidirectional. It basically means if you just want to push data to the server like you're doing video streaming, you'll only have a unidirectional data stream to the server because, yeah, what should he answer to you? The cool thing in SPDY is that a stream can be initiated by either the client or the server. So if the server decides, hey, you need new data, or hey, I need to tell you something, the server can just open a stream into your direction and give you the new data. Also, SPDY streams can be prioritized. So if you have a large site with a large logo or something, you can give the logo very low priority while sending it to the client. So on the web server side, this will lead to optimization on the content delivery. Each stream is identified by a 31-bit stream ID, and stream IDs are organized just in a normal increasing counting way. If the server initiated the stream, it will have an even ID, and if the client initiated the stream, it will have an odd ID, which is pretty cool because if you're reading through a network dump of SPDY, you can just you can instantly see, okay, this one was client initiated and this one was server initiated. By the way, it's pretty funny if you just go to server with an even ID, because it seems like all implementers totally forgot about this part of the specification, and so they will reuse the stream ID for their own stuff, and you might be able to exploit a specific Apache module if you have enough free time. So stream IDs always start at 1. So if you're a C programmer, you have this, yeah, you want to start at 0, but they won't let you. It will instantly reset your connection. At least, hopefully. Actually, if you try to initiate or tried, it's already fixed, a stream with the ID 0 against the Google server, you got a very interesting error message dump. Yeah, you should give it a try, maybe. Streams are, as said, initiated and managed using special control frames. So you can't just go and send data frames on a specific stream ID. You have to actually tell the client, okay, I'm now creating a stream. Please tell me if you want to handle it. And for that, you have the SynStream control frame. The one at the end of the title actually determines the number of the control frame type as used in the header. And SynStream initiates a stream from client to server or from server to client. A stream can be associated to an existing stream, like if you if you request the index page from a server, the server may answer you with the index page and also instantly pushes you with other resources, like you will need the JavaScript, you will need the CSS, and the server side will instantly start pushing it to you and associating it to the specific stream. The stream association is also very important if you use a tabbed browser, because if you have multiple tabs open to one page, SPDY allows to organize these tabs over a single persistent connection. So one tab will be one SPDY stream, and all sub-resources of the tab will be associated to this single stream. The flag actually determines, so SynStream also has a flag field, and the flag on the SynStream actually determines if it's uni or bidirectional. Right now, the only way to do server push functionality is unidirectional. I don't know exactly why, it kind of sucks, but I'm pretty sure they will change it sometimes. So this is how our SynStream looks like in on your network card. As you can see, we have the first bit identifying the frame as a control frame. We have the second part identifying it as a SPDY control frame version 2. The third one is the type for SynStream. The next one is the flag, and the 24-bit length identifier. Each SynStream has at least 32-bit payload on it. In it, you have the stream ID that you want to use. So if you are a client, you will start with 1. If you are a server, you will start with 2. You have the optional associated 2 stream ID. And the next fields are 3-bit for priority. So they actually changed that in draft 2. This is still a 2-bit field, so you only had 3 options for prioritizing your requests. They changed that to 3-bit, so you can do some finer granulation on it. Then we have some unused space, and then comes a variable length name value block. This name value block is pretty handy because it's a representation of HTTP headers in SPDY. Name value header blocks are always compressed using zlib with a pre-initialized direct dictionary. So basically, Google determined what are the most common used words in headers and created a dictionary for the zlib library, which allows the zlib library to do much better compression than without a dictionary. Also, the zlib stream is persistent. So if you send a header to your server and you send another one, you will use the same zlib state. That's pretty important to notice, because that means that if you sniff a connection which is using SPDY, you won't be able to just read or deflate this compressed header block if you haven't all the header blocks that were sent before that point. In this name value header blocks, it's actually illegal to send 2 entries with the same name, which was pretty common in HTTP. So you were able to send multiple header entries with the same name and a different value. In SPDY, the multiple values for the same name are actually separated by a null byte, which is pretty important if your web application happens to use the same header name for multiple values at the same time. You may want to check if you switch to SPDY that your SPDY web server does handle this situation right. You actually have the possibility to have a 32-bit high number of name value pairs, and that means that you can send a lot of data using the headers, and it also means that we can represent all cookie lengths that were possible in HTTP. You know, I think in HTTP the cookie size limit lies somewhere by 2K or something, and SPDY actually allows us to go way beyond that limit. It's important to notice the separation with null bytes if you have multiple values, but yeah. So if you have sent a SYN stream request to your client or to your server in either direction, the other side actually has to confirm that he wants to receive the stream. So that's what this SYN reply frame is for, identified by the control frame type number 2. It accepts the stream and gives additional data about, like if your SYN stream contained HTTP request, it will give additional data about the data with which it will answer, like content encoding, HTTP status code, etc. We will take a look in the sniffer at a later point and see what I mean. The SYN reply block is very small. We just have a stream ID and a name value block, so pretty straightforward. In case of an error, like if you're reusing an old stream ID or something, either side will send a reset stream control frame, which is only used for the abnormal termination of a stream. If everything goes well, you will never see a reset stream frame in your sniffer or something. It only happens on very bad situations like unsupported version. If you do a request with SPDY version 2 and the server only understands SPDY version 3, it will give you an unsupported version error. The reset stream cancel sounds kind of harmless, but it actually means that the other side is not able to handle your request because of resource limitation and so on. So, yeah. And the reset stream looks like this. They actually have a 32-bit field for upcoming status codes, so expect a very long enumeration list for that. So a normal stream termination works like I'm sorry. Works like that. You do a request on the server, and as soon as you have told the server everything you want, you send a frame with the flag fin set. So you say, okay, I'm now done. I'm only waiting for you to tell me that you are done, also done. As soon as you either sent or have received a flag fin, the stream is considered half closed. Half closed means that if you resend data on this stream ID, you will get a reset stream error termination. If you want to terminate a session, you can either just kill the TCP connection, which will lead to an error on the client side, or you can use the go away control frame, which is also very simple and just supports two different error messages. One is protocol error and the other one is okay. To give you a better understanding of it, this is how conversation between a SPDY server and the client may look like. At the top, you have the basic TCP and SSL initialization, like client says to server, SYN, ACK, SYN, hey, how are you doing? And if you want to request a site from the server, you initiate a SYN stream with the flag fin set, because after the request, you won't send any other data. You just want the server to know, okay, give me that data, that's all. And so you will have a SYN stream with the following data in the name value header block. You will have a method like get, post, or head, or whatever. You will have a scheme. The scheme actually determines the kind of data representation you want to use, like HTTP or HTTPS, or maybe in the future also other stuff like, who knows, Gopher or something. Actually, I hope they let Gopher die, but okay. And for sure, the request URL. The server will reply with a SYN reply, hopefully, and will tell you about the content type you will receive. about the HTTP status code, and about the version number. What you see here is actually the HTTP representation on top of the framing layer already, which is what we see on the next slides. And after you have received the SYN reply, the server will just send you the data over using several data frames, and on the last frame it will set flag fin and the stream is considered closed. Doing HTTP requests via SPDY was pretty broken in old versions because you actually ran into problems where SPDY used reserved words which were already used by other stuff, like several web applications used the shim header name already. So what Google did was they added the colon at the front of all reserved words because colons are actually illegal in HTTP headers, so they won't collide with any existing applications. An HTTP request in SPDY must have all these header names set. So you have to tell the server about the method you're using, get or post. You have to tell the server about the path that you're requesting, like /favicon or just / or whatever. You have to tell the server about the HTTP version you want to use. This is, in my opinion, pretty brainless because the only thing you can actually put in there is either HTTP 1.0 or HTTP 1.1 right now, and it doesn't make sense. But okay, you have to send it, so just do it. Another thing is you always have to set the host portion of the request. So you can't just do a request like you would do on HTTP. You can do a non-virtual host request without a host, and you will just get the content of the IP. That's illegal in SPDY. If you do HTTP via SPDY, you always have to supply the host you're requesting this data from. I think this is mainly to prevent some nasty stuff, but yeah. And as said, the shim is either HTTP or HTTPS right now, but as your session is likely to already use TLS, it will mostly be HTTP. So an HTTP response in SPDY looks pretty much the same. You just have two fields that must be present, and that's status and version. Status like 200 OK or whatever, 418 I'm a teapot. Yeah. Interestingly, SPDY also deprecates some HTTP headers like keep alive, because as soon as you're using SPDY, you will use a keep alive connection, because that's how SPDY works. You use a single TCP connection and keep it open as long as possible, as long as your resources allow to. It also deprecates the proxy connection header. That's because SPDY has some own proxy stuff integrated. I won't cover the proxy stuff in this talk because it would just be too much and doesn't really matter right now. And another thing is the transfer encoding. That's something that you never should send via SPDY because it's considered a protocol error. As said, implementations must support gzip even if they don't list it in accept encoding. If your implementation does not support gzip, it's not a SPDY implementation. And that kind of sucks if you try to debug a connection and you just want to have it in clear text in your sniffer. You get crazy, trust me. So as said, compatibility with existing applications is guaranteed with the colon in front of all reserved names. That's new in draft 3. If you use Chromium, you will still use draft 2, at least to my knowledge. And yeah, you may get problems if you do it on an existing web application. So this is how a real request in Chromium actually looks like. I actually copied this from one of the Chromium help screens, because Chromium has some really cool internal sites where you can debug your stuff. Like they will, if you develop with SPDY, they will show you exactly, okay, you send this SYN stream to the server and the server replied with this SYN reply. That's what we'll look at 2 minutes or so. And it's pretty cool. And as you can see, Chromium actually sends an accept encoding header, why ever, even though it's against the standard. And it also submits a host like www.google.com, a method, in this case get, a scheme, and a pass. The user agent, as it's not reserved, is just used as always, and so you can continue to use your nasty Internet Explorer 6 convention hacks. Yeah, and version HTTP 1.1. This is what actually Google will reply if you do that on mail.google.com using a SPDY session, just status 200 OK, HTTP 1.1, and then you will get all the data frames. So as said, if you want to use SPDY, use Chrome or Chromium, because that's the only application that actively uses Chromium right now, uses SPDY right now. And Chrome comes with some very cool stuff. You can take a look at that. Like if I start up a small SPDY server on this machine, something like that, on, yeah, let's say port 8080. And I now start Chromium with the special option, use SPDY, no SSL. It's macOS, it's kind of scary how they try to enforce you to give your application some arguments. You have to use this nasty syntax here. So right now I'm telling Google Chrome to always use SPDY no matter what kind of resource he's requesting on all connections and not only on HTTPS connections. And if I go to my local host on port 8080, I will get a nice message. This is SPDY, this is the standard page that the server delivers. And I can show all active SPDY sessions in Chrome. Actually, this is kind of buggy. You have to do the request twice before it shows up correctly. But you can see, okay, this is the request that Chromium did. You can see that it sends the host header, and you can also see that it's still ref 2 because it doesn't send a colon in front of it. You see it uses the scheme HTTP, version HTTP 1.1, and you get the stream ID down here. So after you've sent the SYN stream request, the server answers with a SYN reply and tells you, okay, everything is cool. Now feel free to go on. And after that, the server just sends you the data over. So the reasons I actually worked with SPDY was that a company asked me to do a black box penetration test on their SPDY server implementation. And the lessons learned during that were there are no tools available for doing cool stuff with SPDY. Like you have to write your own. There's a very old Wireshark plugin that you have to compile against Wireshark source, but it's still Draft 2 and it still doesn't support everything, and it crashed my machine like a lot of times, and yeah, it really wasn't nice. But actually there are two cool server implementations. One is NB-HTTP, a very small Python implementation of SPDY, so if you want to just to do some basic request testing, you should check it out. And there's a server and proxy by Google called flip-in-mem EDSM server. No idea how they actually pronounce it. It's available in the Chromium source, and it allows you to create a SPDY to HTTP proxy. So you can basically request any site using SPDY and just get to know the protocol in your network sniffer. Sniffing a SPDY session is actually kind of difficult because, as said, the whole conversation needs to be sniffed because of the header compression. The reason is that zlib uses a stateful compression state. It's basically if you compress a sentence like hello world using zlib, zlib will optimize its in-memory dictionary for that kind of word. So if you compress hello world again, it will be even smaller. Too bad that this state is not brute forceable, at least not in reasonable time, because it can, depending on the word size you use in zlib, will be around 2 to 32 kilobytes. So if you have ages of time, feel free, but it won't work. So if you don't have the whole conversation, only the data frames will be readable, because there's always a single data frame gzip compression, and won't be a problem for you to just deflate it. But if you try to sniff a live SPDY session, there's actually a way for getting the boost sites to reset their compression. SPDY has a special flag for data frames called, for header frames called flag reset compression. And flag reset compression is thought to only reset the zlib cache on the receiving side and only the receiving zlib state. But actually, at least on my machine, Chromium resets boost states, and as such allows you to inject and read all further communication to the server. I wrote Google about that, like, I think 2 months ago. Don't know if they fixed it in Chromium trunk, but at least for me it still works. Yeah, and at that point you can also become man in the middle if you do R poisoning and something and have a lot of fun. Another thing that the company that I was pen testing the implementation of did wrong was SPDY cache poisoning. They were actually vulnerable for a very nasty way of cache poisoning, because they didn't check the same, they didn't really implement same origin policy for server-side pushes. So if a person goes onto your server with the SPDY, using SPDY, you can actually tell the client that you are like, yeah, I don't know, hugebank.com, and that you are actually providing him with a JavaScript for the site, and that it's that he can keep it in cache for the next 3 years, and you will get all the logins from him, which is kind of cool. So, but Google actually does everything right here, but it still is pretty funny. So, how can you get going with SPDY? Because I had to do this pen test, I had to implement SPDY, and I decided to create a packet parsing and crafting library for SPDY completely in C. It's open source on a 3-clause BSD license, and right now supports draft 2 and 3, and there are also some Python bindings available, and it's completely transport independent, so you can use it on TLS or on TCP, or if you're crazy, even on UDP or something. And it allows very easy creation of tools that speak SPDY, like we have a namespace called SPDY Easy, where you have a very high-level abstraction of all the SPDY logic going on underneath, but still can create cool stuff like SPDY Easy Create Session with a connection struct where you just supply the IP and the port will get you a session. SPDY Easy HTTP request will allow you to do very easy HTTP requests and handle the responses automatically and so on. And there's also SPDY Easy Proxy, which allows you to create very small, very specific proxy tools, like there's a version of SSL strip available for SPDY right now. For those who don't know, SSL strip developed by Moxie Marlinspike deletes all HTTPS from all requests. So if you request a site like HTTP facebook.com and Facebook tries to redirect you to the HTTPS site, it will just remove the redirect. And yeah, there's right now a SPDY version for that available, and it's available at libspdy.org. Check it out. Feel free to give me any further feedback and so on, and have fun with it. I'm sorry that we can't do a practical demonstration. At least I've got this great t-shirt, and thank you. So if you have any questions, yeah?
How does SPDY know that the server, how does the client side know that the server supports SPDY?
There's TLS NPN support, next protocol negotiation in SSL available, and that actually allows you to determine if the server speaks SPDY. And there's also the server can also send an alternate, I think it's X alternate protocol header to inform you that he also speaks SPDY on a port. Google is the only one working on the protocol right now, but as said, I did a black box pen test for a very large corporation which plans to use SPDY for some very large projects, and so I hope that we will see further stuff using SPDY. Okay. I can't really see anything, so.
So in the past decade or so, we've spent a long time working on how to prevent SYN flood attacks on servers using SYN cookies and other methods to prevent clients from trivially wasting server resources.
Yeah.
It looks like with SPDY, that becomes easy to do again. Have you seen how well servers defend against a client just trying to create a lot of streams and waste resources?
Well, actually, interestingly, in the SPDY draft standard, there's a paragraph exactly about that, but in the other direction. They are like, yeah, how do we prevent the server from doing that with the client? And the solution is, if you can't handle any more streams, you can always send a reset stream, or if everything else fails, just send a go away and cut the TCP connection.
Do you see the servers implementing this currently?
No, but there are, well, actually, I don't know what Google is doing on their side, but right now, most of the server implementations are not even fully standard compliant. So, yeah, I know. So, yeah, thank you.